The purpose of this video is to review Module 14 in the Switching, Routing, and Wireless Essentials, or CCNA2 course. So in Module 14, you will review some of the information that you've already learned about routing and configuring routers, but you'll also review how routers determine a best path, how they forward their packets to their destination, the configuration of the basic settings on a router should be familiar to you, but we'll also look at the structure of a routing table and then discuss static and dynamic routing. So one of the purposes of a router is to determine the best path for a packet to take. Now it does this using the information in the routing table. So it uses that information to forward packets to the destination. So the router is going to use its routing table to determine where to forward a packet. And the way I tend to think of a routing table is the same way as a car's GPS. So if you have a car with a GPS, like most of the newer cars nowadays, the GPS knows about all the roads located in particular areas. So if you were to type in an address for a destination, your GPS would look at all the routes that it knows about to determine the best route to get you to your destination. That's the same way that a router uses a routing table. A router has a routing table which is comprised of all the best routes to reach a destination. So once you're trying to reach a particular destination by using whatever command, whether it be ping or whether you're just sending data, then it will go through each of the entries in the routing table, trying to find the best match, and that match would be using the binary address of the IP. So it goes bit by bit to determine which is a longer match, and then uses that particular path to send data. So here you have three networks, the 192.168.1.0, 2.0, and 3.0, and you have two routers. So each of those will have routing tables. If you're looking at your little video here, you can see where R1 consults its routing table to determine the best path for data. So it's looking for something on a 3.0 network, which it disappeared a little bit quick, but it said that the next hop would be over here. So we needed to go to R2. And then R2 looked at its routing table to determine how to send it. Now it's referring to the best path equaling the longest match. So here's an example. So if the destination address is 172.16.0.10, that address is in binary, and the route entries that it knows about, according to what's in its routing table, would be 172.16.00/12/18 and /26. So it would take the destination IP address, put that in binary. Each one of these are in binary, and it's looking for the longest match, which would be here. So it would use this entry. You would do the same thing with IPv6 by finding the IPv6 address and its longest match as well. So if you're looking at this scenario and learning how a routing table is built, one of the very first entries that is done when you do the basic router configuration would be to configure all of the interfaces attached to a router. So in the case of R1, you're going to configure this interface, and this interface. In R2, you would configure this interface, this one, and this one. Okay, and you would do that for each of the routers, and then you would see that listed as either a C or an L. The C would indicate the directly connected network. The L would actually indicate the actual IP address of the interface on that router. And then you may have a remote network. The remote network would be the far network. You can either have the router configured with a static route to reach a remote network or a dynamic route, which would use a routing protocol. And then another option is a default route. A default route, you'll see it listed sometimes as a gateway of last resort. So what this actually means is that a route entry was listed in so that if there is no other match in the routing table to match the destination address, rather than dropping the packet, the router would use this default route. So it says, if you don't know where else to go, go here. So one example of that would be you might be pointing that out towards your ISP, for example. So if your router doesn't know where to send it, it would just send it out to the ISP. If you do not enter a default route, if a router can't find a match in its routing table, it'll just drop a packet. So that's why a default routing entry is usually listed. So here we're looking at the packet forwarding decision process. So once the router determines the best path for a packet based on the longest match, it has to determine how to encapsulate that packet. And if you'll remember from the previous CCNA course, that you have encapsulation in the form of headers that travel along with a packet. They provide information about that packet. So you see what happens here. We have the longest match based on the destination address. Then we start looking at the routing table, and we're looking at the header information. We're looking at the forwarding information for the next hop router. So all of these are described in the figure. So the data link frame with the encapsulated IP packet arrives on the incoming or ingress interface. The router examines the destination IP address and the packet header and consults its routing table. The router finds the longest match in the routing table. The router then encapsulates the packet in a data link frame and forwards it out the egress or exiting interface. The destination could be on a directly connected network, or it may have to go to the next hop router. If there is no entry, then the packet is dropped. So that's kind of the process that it goes forward. So if a packet is being sent to a device on a directly connected network, it will need to determine the destination MAC address associated with the destination IP address of the packet. So that would kind of vary depending on whatever scenario. Let me see if I can go back and I will talk about that a little bit. So if you remember from the previous course, for example, so we have PC1, R1, R2, R3. So if data is traveling from PC1 to R1, okay, and its intended destination is going all the way over here to PC2, well, you're going to have various MAC addresses throughout. Okay, every time it enters one interface and then exits that device, you will have a different MAC address, but the IP address will remain the same. So again, if you're pinging from PC1 to PC2, then the source IP will be 192.168.1.10. The destination will be 192.168.4.10. But the MAC address leaving PC1, heading in this direction, will be the source MAC will be coming from PC1, the destination will be R1. Okay, once it's received on this interface, well, then it has to be repackaged before it goes from R1 to R2. Now, the source and destination IP addresses will remain the same because it's still going from PC1 to PC2, but now R1 becomes the source MAC, R2 becomes the destination MAC. Same thing as it's received on R2, it's received on layer 1, then it checks the destination address or layer 2 address. Okay, that matches, but layer 3 address does not match, so it needs to repackage it before it leaves R2 to go to R3. R2 will be using the same source and destination IP, but the MAC address will be going from R2 to R3. And then once it reaches R3, it will be repackaged. R3 will be the source MAC address, PC2 will be the destination MAC. And then once it reaches the destination, we'll go all the way up the OSI model onto PC2. So that's kind of that process in review that was discussed in the other CCNA1 class. So if you're looking at your various decisions, it can forward a packet based on a directly connected network. It would use the next hop router like you just saw, or if it drops the packet because it doesn't see that in the table. So those are the various options. And I kind of just discussed all of these different links through here. So if you were not clear about the way I just described it, feel free to use the links in the videos there, and they might it might be a little bit easier to understand. So the primary responsibility of packet forwarding function is to encapsulate the packet and to send it out the interface, and it's encapsulated for whatever type of data link that it is on. So for example, if it's Ethernet, it will be encapsulated for an Ethernet frame, or if it's using some other protocol, it would be wireless, for example, would be using that. Now, routers support 3 packet forwarding mechanisms: process switching, fast switching, and Cisco Express. Process switching is an older packet forwarding mechanism. Now, when a packet arrives on an interface, it is forwarded to the control plane where the CPU matches the destination address with an entry in its routing table and then determines the exit interface and forwards the packet. So the router does this for every single packet, even if the destination is the same for a whole stream of packets. Therefore, this is a slower process, so it's not really used in today's routers. Fast switching is another mechanism. It is still an older packet forwarding mechanism that's used. It uses a cache system to store next hop information. So when a packet arrives on an interface, it's forwarded to the control plane where it searches first in the cache. If it's not there, then it is kind of process switched and forwarded to the exit interface. So the information is all stored in cache. If another packet happens to go in that same destination, it arrives on that interface, it just goes directly to cache, reuses that information. It makes it a little bit faster. So it takes longer for that first packet, but then after that, it becomes much quicker to process. With Cisco Express forwarding, this is the most recent type of packet forwarding. So similar to the fast switching, the Cisco Express forwarding builds a forwarding information database and an adjacency table. The table entries are not packet triggered like fast switching, but they're considered what's called change triggered, such as when something changes in the topology. So when you have a converged network, this particular forwarding information database and adjacency tables contain all the information that the router needs in order to forward a packet. So it's the faster forwarding mechanism, and it is now the default on Cisco routers and switches. So your basic router configuration should be nothing new for you. So if it's been a little bit of time, here are your configuration examples. So you're going to do your enable config t, host name, your enable secret. Remember, your enable secret is encrypted and it's more secure than enable password. You are going to put a password on your console line and your VTY lines. Now, both of those are considered plain text, so therefore you would enter this service password encryption to encrypt those passwords. Banner MOTD, banner message of the day. So that gives you the banner that you would see when you're first logging into a device. If you're using IPv6 addresses, you will need to enable that with IPv6 unicast routing. Configure your addresses. You can configure both an IPv4 and a v6 address on an interface. The way IPv4 and IPv6 work is that IPv4 addresses talk to other IPv4 addresses, and the same way with IPv6. They talk to other IPv6 addresses. You have a global IPv6 address. Okay, so this can be used outside of a network, whereas the link local address is used on a particular link. The descriptions that you see don't affect the functionality, but they do make it a little bit easier when you're looking at your output. For example, doing a show run on a router interface, you can tell that this is a link to LAN 2. So here we have a serial interface that is configured, and then copy run start, which is the equivalency of going to file save, say in Microsoft Word. To verify your commands, you have a lot of show commands. Show IP interface brief. This will give you a brief picture. It will give you each of your interfaces on your device, and they will also show you the IP address and whether they're up or down. Show running config interface specifically gives you information about a particular interface. You have show interfaces, which gives you information about all of your interfaces. Probably more detail than you'd want to know. Show IP interface and show IP route shows you your routing table, and then you have ping. For each of these, if you wanted to look at IP version 6 information as opposed to IP version 4, just replace the IP with IPv6 in the command. So looking at each one of these, show IP interface brief. So again, it shows you your IP address and whether the status and protocol are up. So this usually indicates layer 1, that you have a cable connected to it, and then this is your protocol. So in the case of having an up and down status, you could have layer 1 up, so you have a cable connected to it, but maybe you forgot to enter an encapsulation, and then the protocol could actually be down. Ideally, you want to see an up and up status anytime you have a cable connected and have an interface configured with an IP address. Show IPv6 interface brief looks similar, but you have your IPv6 addresses. Show run is what you'll want to use to look at the entire running configuration. This is stored in RAM. Show interfaces will give you information about all of your interfaces. Show IP interface as well will give you information about a particular interface here. Show IP interface gigabit Ethernet G000 or gigabit Ethernet, 000. And it gives you detailed information. So why would you want to look at this? Well, you could look for specific information if you're looking for the number of errors that might be occurring. You see here some multicast information. There may be other information you're looking at as well. Show IP IPv6 interface gives you specific information about this particular IPv6 interface. Show IP route is your routing table. Show IPv6 route is the routing table for an IPv6 interface. Then you have ping. Okay, so this is testing for connectivity. You're pinging and you're looking at the output. Ideally, you want to see the success rate at 100%. Now, if you've just configured it and your success rate is at 80%, that means it was probably issuing that ARP request at the beginning because it didn't know both the IP and the MAC address. If it's at 80%, I would use your up arrow because it's going to show your last command in your command buffer. And so up arrow and ping it again. That'll reissue the same command. Should be at 100%. But that's just a little shortcut. You can include all kinds of like filtering whenever you're issuing commands like show running config or show run in the pipeline, section line, VTY. So you want to see just VTY information instead of all of show run. Same thing here, you're looking at IPv6 interfaces, you will only want to see the up interfaces. You can do that. So there's lots of filtering information that you can add there. When you're looking at a routing table, here we have show IP route. With show IP route, it tells you all the information you need to see about a particular router. So this is everything that that router knows about. When you're configuring your devices, you want to make sure that each router knows about all the routes that are available. If you're looking at this, you configure R1, you configure this interface, and this interface. Okay, so then ideally you would know about the network attached here, the network attached here, and the network attached here. But you don't know about, or your router doesn't know about, the 4.0 network or the 5.0 network or what's here. So that's where the routing table information would come in. So you would configure information about the directly connected devices. R2 would do the same thing. And then you would either use static entries to tell R1 about these remote routes and to tell R2 about these remote routes, or you would use a dynamic routing protocol. Dynamic routing protocol would allow these two to share their knowledge with each other and build their routing table databases. Static entries will be manually configured, and you will tell the particular device that there is a 4.0 network. In order to reach it, you're going to have to go from here to get to the 4.0 network. So here's some routing table principles that you'll need to know. Every router makes its decisions alone based on the information it has in its own routing table. So you can't assume that because one router knows about information that another router would know about it. You have to look at each individual router when you're troubleshooting. So the information in one router also does not have to match the routing table information of another because they all have different routing table entries. Also, just because a router knows about a path to get to a destination doesn't mean it knows how to return. So that is something else that would have to be added in. So for example, if you're traveling from one place to another, you may have directions to get there, but you also need directions how to return. You may not be able to use the same exit numbers that you use to get there, so therefore you would need return information. So that's where if you ping a device and it's unsuccessful and you trace route, you see the route getting there, but it's never leaving and returning back to the source device, then you'll know that it doesn't know about the route back, and you'll want to check the routing tables of the other routers. When you're looking at the routing table information, you will read it like this. So how did you learn about it? This is the first part, whether you're looking at IP version 4 or version 6, how the route was learned. So if it had a C, it would be directly connected. This is the destination network. So where do you want to go? This would be the administrative distance and the metric used to calculate that routing table entry. The administrative distance is the trustworthiness of a route. So the O indicates OSPF, and the only reason I know that is just because I haven't memorized. It is always 110. But for different routing protocols, they would be different numbers. For example, EIGRP would be a 90. Okay. Directly connected have an administrative distance of 0 because they're the most trustworthy. Static routing table entries are a 1 for the administrative distance. And then when you start using routing protocols, the numbers tend to get higher because the devices are configuring those instead of those being configured by a network administrator. So again, I learned about this according to the code that's here. It would be OSPF. This is the destination network. The administrative distance for that particular method that's being used over here. It's metric. I get there through this route. I learned about it this long ago, and this is the exit interface on the particular device that I'm on. So if I were to look back at all of this, so 10.0.40 is the remote network. Okay. So we're trying to reach this, and I'm over here in R1. So in order to get there, I would need to exit S011 and go to 10.0.32. So that's probably what this is, yes. So in order to get to 10.0.40, we're going to go to 10.0.32. We're going to exit that interface. So that's how you would read it. Again, directly connected networks are going to be indicated with a C. So the directly connected interface would be the interface, the network on that particular router. The L would be the actual interface on that router itself. So it would be G000, which would be 10.0.11, which means we are actually connected to 10.0.10. So going back up here, so 10.0.11 is this interface, and because we have an interface on this network, that makes us connected to that network. You can use your show commands in order to see the entire routing table. You see that show IP route or show IPv6 route. Now, static routing, it has its uses. You might think it's easier just to have a dynamic routing. The router will automatically change according to whatever has gone on with the network. Static routing, you would need to configure that yourself. It does make routing tables smaller. So when routing tables are smaller and your router is having to go down routing table entries and try to match them towards the destination, that can take a little bit of time. So the smaller the routing tables are, the better. You might have to use a static routing for a default route that I mentioned earlier. So if you're routing traffic to a specific destination or it's always going to that destination, a default route might be the easiest way to go. Or to and from a stub network. A stub network is a network that's accessed by just a single route. Okay, so stub routers right here, this would be a stub network. It's only going in one direction. So I'm sorry, over here, be a stub network. So you're only going in that one direction there from over here. If you're configuring static routes, that'll be done more in module 15. But the way that you would configure that, if you're looking at R1 and you want to reach this 10.0.40 network, you would configure using the following syntax: IP route, the destination network of 10.0.40, its mask, and you can tell that from a /24, the mask is equivalent to 255.255.255.0. And then this would be the next hop. So if you're going from R1 to R2, this would be the next hop. So IP route, destination mask, destination network, its mask, and the next hop. Same way with IPv6. IPv6 route, destination network. You don't have to worry about the mask. You just use a slash notation with IPv6, but you still enter the next hop address. If you want to see static routes only, when you're doing your show IP route, looking at the routing table entries, the command is show IP route static or show IPv6 route static. Again, as I mentioned with dynamic routing, the nice thing about dynamic routing is that you enter the information that router is attached to. So it's configured with this, and this one. R2 is configured with these interfaces, and you would issue a command for them to share their information. So when you look at it, you'll actually have codes. Now, I knew it was OSPF earlier because I had memorized the administrative distance, but you also have a code here that shows you that that was OSPF. If it were EIGRP, it would be indicated with a letter D. Why a letter D? Because D stands for Joule, which is the algorithm that calculates EIGRP routes. A default route can be used as a static route entry. It's a route entry of 0000, or we call it quad 0. Okay, so that means nothing needs to match in your default routing entry. You'll see it listed with like an S and an asterisk, and you see all zeros, which looks a little strange. But basically what you're saying here, if you're going from R2 and you want to go over here, you can do a static entry just to tell all the traffic to go in this direction or go in this direction to the ISP, and I believe that's what they're doing here. Yeah, they're pushing it all out to the ISP. So quad 0 via 209.165, 200.226. So yes, go in this direction. So really when you configure that, earlier where we did the IP route space destination network, it's mask in the next hop, it's IP route 0000, 0000, and then the next hop address. So it's pretty easy actually to configure that one. Looks a little strange. So if you're looking at your routing table for IP version 4, you will see a major network address. So this is a class A. You can tell that's a /A. These were all subnets off of that one. So that's why they're indented underneath the major network. Notice it says it's variably subnetted with 8 subnet masks and 8 subnets and 2 masks. It's variably subnetted means a VLSM. If it said subnetted, it would just be traditionally subnetted, but you probably wouldn't see that anymore because most newer devices, and I say newer as in, the last 15 years or so, 15, 20 years, are variably subnetted. They support VLSM. Again, they're indented underneath the major address. Same thing with IPv6 routing table. You will see each of the entries. You see C's and L's and O's. This is how they were learned. You see the destination address, the metric. See, the metric is 0 because it's directly connected. And then you will have the next hop. Again, administrative distances are the trustworthiness of a route. As I mentioned earlier, this is your whole table of your administrative distance. Directly connected would be a 0. Static entries would have a 1. And then they go from there based on whatever routing protocol you're using. You see you have higher numbers. So static and dynamic routing are both being used. Dynamic routing would be great if you have a lot of routers, more than just a couple of routers. They automatically change with the topology, so they're easier to scale or scalability as your network grows. They would automatically change for that. Static routing is great if you need a default route to get to a particular service provider, or if you don't want If you don't want a particular route to be advertised, as would have done with a dynamic route, you would enter a static route. Also, if you want a route to travel towards a specific destination or on a specific path, you can configure that. Or, as we mentioned earlier, between stub networks. So all of those would be cases for static addresses. Make sure you review this chart on the differences between static and dynamic routing, because you will need to know that. I mentioned the scalability, topology changes, configuration changes. With static routing, you would have to configure every single change, but dynamic would automatically change for that. Security, you have more security with static routing, because again, with dynamic routing, it's going to share all that information with another router. So it's going to take up more CPU resources when the router is having to determine this for itself, but that's not required with static routing. Static routing is more predictable path. Dynamic has a tendency to change. That could be positive or negative. Dynamic routing has changed over the years. You will see these versions kind of in summary here. You had version 1 of various protocols. Version 1 did not support VLSM, but you'll see that in version 2 of these protocols, they did support VLSM. Version 3 supports IPv6. In a nutshell, that's the differences between versions 1, 2, and 3 of each one of these. Now, if you're looking at your dynamic routing protocol, the routing protocol uses a whole set of processes, algorithms, and messages to share information. So the routing protocol includes information about remote networks, maintaining and updating routing information, choosing the best path, and finding a new best path if a route goes down. It includes information about various data structures. So it might use tables or databases. That information is all stored in RAM. Most of this was beyond the scope of the CCNA2 course, and a lot of that would be in the CCNA3. So routing protocols also use messages. There are various types of messages they use to discover a neighboring router. They might be multicast type messages. They could use other types of messages to communicate with each other, advertisements, that sort of thing. It's particular to each type of protocol. One other thing that is used by a dynamic routing protocol would be an algorithm. An algorithm is a list of steps that are used, and these algorithms help each routing protocol determine the best path for data. So again, that's something you would learn more specific when you get into your routing protocols and configuring those, such as OSPF or EIGRP, for example, in the CCNA3 course. So if you're looking at common dynamic routing protocols and their metrics, for RIP, for example, uses only hop count. A hop count is each device that data passes through, so that would be each router it would pass through would be considered a hop count. And RIP adds a path based on the hop count. If it determines that a route is too far away, it uses the hop count method, and it would start with an counter that would increment down from 16. So once it starts at 16, then it would do the next 15. So it would go 15, 14, 13 down to 1. When it reached 0, it would assume that the route is too far and just drop the packet. OSPF uses a cost method, and that's based on the cost value of a link. Okay, OSPF, the cost value is based on that particular link, and the link cost is based on the speed of the link. So faster links have have a different cost value, have a lower cost than slower links do, and you would prefer the faster links and the lower cost value. EIGRP uses metrics based on bandwidth, load, delay, and reliability, so it takes several things into factor. Now, one thing that could also be used by routing protocols is load balancing. So, equal load balancing can be used if there are multiple routes to a destination. And the load balancing would allow data to travel in both directions to the destination and kind of balance out the amount of data that's being sent on a particular path. So again, there are several different features there. What you would need to review about this section, there's a lot of information, but scrolling back up, you'll want to know the functions of a router, how best path is determined, how a routing table entry is written, and how to be able to interpret that. What you should be able to do when you look at a routing table is go to the routing table of each particular router, and you should be able to piece together a diagram of the particular network just by looking at the routing table, even if you don't have any visuals there. You should be able to do that based on the routing table entry once you get comfortable enough for that. But understand how data moves from one end of the network to another. Know your basic routing configuration commands, routing table principles, the difference between a static and a static dynamic route. Know what a default route is. Okay. If you know all of those, then you'll be well prepared for your Module 14 quiz.